Welcome, everybody. So today we are hosting a public lecture by Dr. John Platt, and this is co-hosted by the Data Science Lab and by the Center for Sustainability. And John Platt is a distinguished scientist at Google Research, and I got to know John because of his work on machine learning applied to climate change, and this is also what his talk will be about today, focusing mostly on the airline industry. But he's actually known for many impressive achievements across computer science, machine learning, and actually many related disciplines. And for those studying data science, something that John invented is sequential minimal optimization, which is actually making support vector machines train. So he was one of the people inventing things around support vector machines. And for everybody else, John discovered 2 asteroids, and he also is a recipient of an Oscar, of an Academy Award, for his technical contributions. So without further ado, let's welcome John.
Thank you, everyone. Can everyone hear me? Is this good? Okay, everyone's nodding. Great. Well, I'm happy to be here. I'm going to be giving a talk today about how what's now called artificial intelligence can be used to boost the power of remote sensing, and then we can use that to fight climate change. Now, in this talk, I always like to start the talks if you're not into climate change. I guess we're all into it because we're all being subjected to it. But if you're not into the technical details, I like to give some climate background just to explain why we chose to work on the problems that we did. And then the most of the talk will be talking about artificial intelligence methods to fight jet contrails. Those are those white linear clouds you see behind jets when they fly up in the stratosphere. And then I think we have time, yeah. I'll talk a little bit in a little mini extra talk about how you can use artificial intelligence to help homeowners decide to install more solar panels, and that's also helpful for the climate. So let's talk about the background of climate change. So really, I like to start with this slide because for centuries now, the total amount of energy consumed by humans on the planet has been growing exponentially, but slowly, about somewhere between 1% and 2% per year, even if you go all the way back to 1800. And if you think about that and you understand economics, you realize that that the level of energy, the more energy that people use, the more prosperous and healthy they are, and sort of the better off society is. And that's you can argue that the developed nations have decoupled their energy and their GDP, but for the vast majority of the number of people on the planet, it's still quite coupled. So this would be the ideal state, that we will keep growing the amount of energy until the end of the century. I made this slide a while ago. In 2017, there was about 18 terawatts, continuous 18 trillion watts of power consumed by all humans. And that will keep growing by a factor of 6 until everyone uses roughly the U.S. power per capita rate for the 11.2 billion people that are projected by the UN to be alive in 2100. This would be optimal, and I think this would be a very happy world, except there's no possible way we can grow the amount of energy by 6x and with fossil fuels. That would utterly and completely cook the planet. So it would be great to stay on this line, but there's this giant problem of burning fossil fuel to get there. So why are fossil fuels bad? Well, there's something called the greenhouse effect. You might not realize it, but the greenhouse effect actually helps keep the Earth habitable. All these numbers are in milliwatts per square meter. Most of the heat, the warmth in watts per square meter. Most of the heat that you feel when you walk outside is actually not necessarily directly from the sun, but actually heat energy you feel from the atmosphere. Water vapor and carbon dioxide actually absorb infrared radiation that's coming out of the ground it gets absorbed by those trace gases, and then it gets re-emitted both out, up and down. And that actually keeps the Earth's land and ocean surface to be about 14 Celsius. And that's a very comfortable. If it weren't for the greenhouse effect, we would be living on an ice cube. So the problem is that the trace gases, there are not very many of those trace gases. And so therefore small amounts, i.e. only billions of tons, if you alter that, which we dump in billions of tons of greenhouse gases every year into the atmosphere, that actually alters this, this radiative balance and warms up the planet. So that's not good. Now, there is a climate crisis that is occurring right now, because once you emit carbon dioxide from a tailpipe or a factory, some of it gets reabsorbed very quickly into the ocean, into the biosphere, about half over the few years after you emit it. But the remaining stays for centuries or millennia. So in effect, you can think of it, the atmosphere as a finite resource. You can only put in a certain amount of carbon dioxide or other greenhouse gases before it just raises the temperature. So there's like a fixed budget. That's sort of what you can think about, at least on the multi-decade time scale. And here we are. These numbers, the rough numbers change as people update their models, but this is still correct, even though it's a few years old. It's from the SR15 report. And so this is just the business as usual graph, where the amount of greenhouse gases slowly increase with time, the rate. So this is measured in gigatons. Those are billions of tons of CO2 equivalent. And as you keep going and keep emitting, there are just points of no return, right? Around 2030, if we just keep going on the current path, there's no way, well, we'd have to essentially stop instantly, which is not practicable. So once you pass this thing, you've overshot 1.5 Celsius, which is, considered to be the edge of dangerous. And this is the target for the Paris 2015 Accord. Sometime in the 2040s, we will pass the point of no return for 2 Celsius, and then we'll pass other points of no return later on in the century. But even 2 Celsius is considered dangerous, and that we have to do everything we can to keep the global mean temperature 2 Celsius above pre-industrial. We're very close. This year this is more of an average. You're supposed to take a temporal average and not look at one season. But this year we may have already breached the 1.5 Celsius for 1 year because of El Nino. Now the trouble is, human society, many of you are policy people, that human society does not turn on a dime, especially considering that there are literally trillions of dollars of infrastructure built, right? So let's pretend we have the St. Augustine moment in 2030, and we say, in 2030, no more. We're not going to build any new fossil fuel infrastructure. We'll let the old stuff decay away, but nothing new. Well, approximately, that's equivalent to having an annual reduction of about 3.3% emission rate. In other words, just as the old stuff, the old cars decay away, the old factories decay away. And so you can see there's a lot of inertia left over, a lot of emissions have been baked in. So even though you think you might be stopping at 1.5 Celsius, even if you say no new fossil fuel infrastructure, you end up about 0.7 Celsius above that. So that's already kind of baked in. If you want to be very radical and go and just actively destroy fossil fuel infrastructure, you might be able to get 10% annual reduction. That was sort of the reduction that we got during COVID. Every year, not just for 2 years, even though it was kind of terrible. And there you get an overshoot of about 0.3 Celsius. So it's not only are we running out of space, we can't turn the entire human civilization on a dime. So we're really running out of time. The other way of plotting it is when do we get that declare no new fossil infrastructure? If that's the route we're going to take, not going to be radical. We've already kind of passed the 2 Celsius point, just barely. And so, as we delay year by year, we're going to get 2.1, 2.2, hopefully we'll stay below 3. but it's going to be kind of a knife fight for every tenth of a degree Celsius between 2 and 3. And you really don't want to be above 2 because there may be, first of all, there are very serious health effects and damages just caused by that. And then there are these risky but very difficult to quantify tipping points that no one exactly knows where they are. So you really don't want to go past 2. Now, the problem is, I sure wish there was a silver bullet. I would love to stand here before you and say, ta-da, the answer is fusion. Well, maybe, I mean, but you know, since we don't have fusion energy, you know, the sources of greenhouse gases are shown in this graph. And there are many, many sources. In fact, these are just the major sectors, and within each of these sectors has a lot of subsectors. So, for example, this is a worldwide graph. Transportation has light vehicles and ships and planes. So, and industry, there's many different sectors. So there's no one, if you're trying to just reduce emissions, which we should do, there's no one magic silver bullet that fixes everything. It's got to be a lot of work and a lot of technologies and a lot of policies to try to cover this entire pie. I call this the pie of sadness. Now, there are some things that are, I'm not claiming they're easy, but they're less difficult. Renewables are an incredibly good path. They're getting cheaper and cheaper because of the learning curve, and so that's great. And so we can try to electrify as much as we possibly can. It's relatively easy to detect methane leaks from oil and gas infrastructure. We can turn that off. Electrifying cars and trucks seems to be proceeding very well, and electrifying heating and getting heat pumps. We were just talking about heat pumps are getting very popular, so that's less difficult. There are definitely more difficult things, like what do you do about industrial heat? In industrial heat, that's like the process heat you need to run manufacturing. You're competing against raw fossil fuel. So essentially, you know, a flame of natural gas is very, even here in Europe, it's still really quite inexpensive, and it's very difficult to compete with that. Steel, concrete, air flight's very difficult to decarbonize. Getting rid of the carbon in the last 10 to 20% of electricity is quite difficult, and I can go in and explain that if you like. Just animal agriculture is very difficult to mitigate. So for this talk, I mean, we've thought about a lot of this, but for this talk, I'm going to tell you how artificial intelligence can help the things that are highlighted in red, namely air flight, not necessarily carbon, which is very difficult, but there's another source of heating that I'll talk about with contrails. And then again, in that last mini talk, I'll talk about maybe we can start eating into the last 10 or 20%. It's actually very difficult to model, but at least it helps renewables. So let's start talking about aviation emissions. So we're going to zoom into that part of the pie of sadness. Now, as you've seen, jets fly up and they fly to what they call the top of the troposphere or the bottom of the stratosphere. The troposphere is the part of the atmosphere that has weather. The stratosphere is the very quiet part that doesn't convect above that. And so they fly right at the edge. And what do they emit? Well, the standard way of thinking about it is they emit carbon dioxide and nitrogen oxides, which right there themselves are greenhouse gases, and that's really well understood. But something interesting happens when you fly. You also emit little tiny bits of water vapor, which then freeze because it's quite cold up there, and little bits of soot. And normally, maybe you get a pretty little stripe, which are what they're called condensation trails or contrails, and that you would think is like just a harmless, pretty cloud. But it turns out there are parts of the atmosphere that are so-called supersaturated in ice. And supersaturation is, you may have seen it if you ever try to make candy. You know, when you take hot water and you add so much sugar to it, it's called rock candy, that it supersaturates, so that if you even take a little bit of candy, the whole thing precipitates out and turns into a big rock of candy. I don't know if you've done that. Same thing happens in the stratosphere or near the stratosphere, that just because the way weather works, if it were supersaturated with respect to water, it comes out as a little cloud. But it turns out the vapor, maybe this is technical, but the vapor pressure of saturation is different for ice and water. So there are humid parts of the upper atmosphere where it's just waiting for soot or little tiny ice particles. And then like a gram of ice gets emitted by the plane, and then 10 kilograms of water vapor gets sucked out of the atmosphere. So it's this 10,000 to 1 ratio. And when that persists, that's a problem. And the reason why so this is sort of what I'm explaining, that you've probably seen pictures. Here's a picture from London. They can actually just persist, these clouds can persist for hours and grow. Here's a satellite image from France. And in fact, Europe has so much air traffic that unfortunately you all have some of the densest contrails. At least some of the modeling says that, several percent, there's large error bars, but, several percent of your skies are actually covered by contrail cirrus, because it kind of grows from these lines. You can see how they get bigger, and they kind of turn into kind of this sort of blurry cirrus cloud. Again, you would say, so what? So there's a cirrus cloud. The problem with the cirrus cloud, there's two opposing effects, but they're mostly bad. The bad, well, let me talk about the good effect. The good effect is that they're white, right? So during the day, they're a little bit like geoengineering, that the sunlight comes in. So we're doing inadvertent geoengineering, right? Sunlight comes in, and a little bit of it bounces out to space. That's cooling, but only during the day and really when the sun is high. 24 hours a day, the Earth is what they call a black body emitter. So the Earth, I was talking about this in greenhouse gas. The Earth always emits infrared radiation. Just any object emits infrared radiation at the temperature, with a spectrum corresponding to a temperature. Max Planck figured that out. And unfortunately, in that radiation band, which is around 10 microns, the contrail absorb. They're like black in that frequency, and so they absorb the infrared radiation and then re-emit it up and down. So they actually act as a blanket. And on average, they're much more warming, because this happens everywhere all the time. That only happens when the sun is high in the sky. So on average, they're warming. So when you cover Europe with a lot of contrail cirrus, you are warming Europe up by a fair amount. Now, how do you measure this? One way of measuring, one thing I've learned over the last several years about working on climate change is all about accounting, sadly. And it's all difficult because there are a lot of uncertainties. But one way to account for climate change is sort of forward-looking 100-year impact with a metric called GWP 100, because CO2 goes in the atmosphere, as I said, and it lasts for centuries. Contrails, they show up, they last for 6-8 hours, and then they go away. So they're very strongly warming for 6 hours, but then they go away. Then the next plane comes, and the next plane comes. But if you average over like all of the flights of a year, contrails do about 1/3. If you convert it back to the equivalent CO2 in terms of the equivalent number of joules of warming over this next century, even though the CO2 is lasting for a century, it's still about 1/3 of the total warming. So it's a very significant effect worldwide. This is worldwide. And over Europe, it's especially terrible. Let's see. Oh, okay. So I'll tell you about Europe in a moment. But it's really hard to avoid. It's very difficult. You're trying to make this piece of metal go hundreds of kilometers an hour, right, up in the sky. That takes a lot of energy, and it's difficult to get that in a non-fossil fuel way. People are working on sustainable aviation fuels. It's kind of a mess. It's difficult. Contrails are much easier to avoid, because remember I was telling you there are these regions of supersaturation. Those tend to be thin. They might only be 100 meters thick. Sometimes they're kilometers thick, and that's unfortunate, but they might be hundreds of meters thick. So all you need to do is have the plane fly below, or sometimes around. If they're kilometers thick, you have to fly around. But if they're only hundreds of meters thick, you just go down and go back up again, and you've avoided making a contrail. So it's much easier for the airlines to avoid warming with contrails than to try to adopt sustainable aviation fuel or hydrogen or something wild. So they're very excited. The airlines are actually very excited to work with us. I'll tell you about a study that we did with one of the airlines. Now, to sort of reiterate, not all contrails it's not like CO2. CO2 is just CO2, and it causes a sort of a fixed amount of warming. Not exactly, but in roughly constant amount of warming. Contrails are very, very different. They depend, if the contrail occurs on top of like below a cloud or above a cloud, it changes the amount of warming it puts on the Earth. during the day, hour of the day, it changes. Time of year, it changes. So it's all very difficult, and we'll talk about how we manage this. Here's a fun graph that might frighten you. This is again using a model simulation because obviously contrails occur where flights occur, and of course there are many. Of course, there's also over North America. I'm not blaming Europe, but if you look, it's the European airspace is very dense, and in fact, I mean compared to Madagascar. If you look at the graph here, it's more than a watt per square meter of instantaneous radiating forcing. I'll explain what that means. Just to get you calibrated, all of anthropogenic warming is only about 2.9 watts per square meter. So just locally over Europe, contrails can be a substantial warming effect. So they may be actually melting your glaciers. Now let me, again, put the asterisk in. Not all watts of warming are identical. This is still an open research topic with lots of arguing, but it seems to be contrails are roughly 40% as effective, at least according to the climate models, as CO2. So it's not quite 1 to 3, it's more like 1 to 12. But still, this is a potentially easy to change thing that might be several percent of the warming over Europe. And in fact, we're starting to work with the Eurocontrol, the European-wide agency for doing air traffic control. They're very interested in avoiding contrails. So maybe we can actually help the local climate in Europe. That'll be exciting. Or it's sad that contrails are affecting it, but it's exciting to help. Okay, so how do we use, so now we've established that contrails are a bad thing. How can we use artificial intelligence to reduce contrails? As I had mentioned, you make flight adjustments. Now, it turns out these ice supersaturation regions are not that common, fortunately. Only depends exactly how you measure it, but only 3% of all of the flight kilometers make almost all of the warming. So if we can make an AI system to predict which 3% of the kilometers, then we can suggest that people go down and then back up again. That's what they mean by these conditions exist only at specific altitudes and temperatures and high humidity levels. So again, we have this. We've made an AI system to predict contrails both kind of in real time and either a day in advance, or you can do it climatologically months in advance, although it's not so accurate. And then you can make small adjustments to the route to avoid warming entirely. So the system that we built is a little bit complicated, so let me try to go through the architecture of the system. So what we want to do is help the airlines avoid contrails. So what do you need to help them? You need two things fundamentally. First, as I was alluding to, you need contrail prediction. So what we do is we take the weather data. Actually, we take the weather data from the ECMWF, which is the European medium-range, long-range weather predictions. Those are, I can get into it if you would like to know more. Those are actually slightly biased and not quite right when it comes to humidity up by the stratosphere. So we have to kind of fix it up with machine learning. But we built a contrail predictor to predict these regions, which we call contrail likely zone. We also need a contrail verification. This is sort of like if you're into climate change MRV, measurement reporting and verification. In order to do an experiment, or in order to actually have a regime where you actually avoid contrails, we need to know which planes made which contrails. So that, for example, we've done, I'll tell you about in a minute, an A/B study where we asked some people to go down and not. So we wanted to know, like, when we did an intervention, when we asked to do this experiment, did it actually work, and did the planes we move actually make fewer contrails? So it's very good to go back and assign, yes, this plane made this contrail. And so we have a system that takes the flight data and estimates that. That's not as easy as you might think, because I'll show you this. Essentially, we look from the satellites, and the satellites have pixels that are around 2 kilometers across. And so the contrails are very small in the beginning, and then they grow. So it takes about 15 to 30 minutes before you can see them. So we have to kind of match contrails, which are moving with the wind, 15 to 30 minutes back to where the flight flew. So there's some matching there. And that all depends, right, on something upstream called contrail detection. So we actually can look in these satellite data, find where the contrails are, and feed it into the contrail verification system. We also use this as training data for our AI. In other words, we say, we gather a very large data set. Yes, we saw a contrail in a satellite. What weather caused those contrails? So it's the training data for the prediction system. So yeah, there are these different pieces that fit together. Here is an example. You may not know where Detroit is. Detroit is just around there. But yeah, and it might be very difficult to see. There are these linear features that are drifting. This is from the satellite image in the long wave IR, infrared. And you see clouds, but you can also see, I don't know if you can see, like these here. These are contrails that were generated in drifting south. And our friends in the airlines were up in the sky, and they took the same pictures of the same contrails, so we can actually see them both in the satellite image and from the planes, or from the ground. Although satellites are ubiquitous, so we watch it the whole time. And they're seen from I mentioned this before, the geostationary satellites. In case you don't know, there's one orbit called geostationary, which exactly orbits the equator in 24 hours. That's just its orbital period. So it appears as if it's just floating above a spot on the Earth. So this is how all the weather satellites work. So we just take the weather satellites, and you get one picture every roughly 10 to 15 minutes. 2 kilometers is what we need. Over Europe, there's a new satellite that was just launched called Meteosat 3rd generation, which is actually good enough for us to use, which is 2 kilometers. So that's good. And so what we did is to train the detector. We've actually open sourced this data set. We have a data set of 24,000 images, 9,000 of which have contrails. Then we asked people, we had these judges, essentially as part of this, we have an infrastructure in Google to do this. We asked our judges to label in these images where they saw the linear clouds. And so they carefully kind of drew where they saw linear clouds in all these contrails, and that's the training set that we used for an AI system to build the contrail detector. And we had a Kaggle competition. If you don't know about Kaggle, it's a platform where people can compete to make the best. They compete to make the best system for something. If you set up a competition, so that we made a competition where people actually beat us, which is nice. They found a bug in our data set, so they figured it out and actually beat our system, which is nice. The way our system works is it kind of makes sense, right? Remember that image over the United States of the contrails drifting? If a neural network can see multiple frames, remember this is every 10 minutes, so if you see the last hour and watch the lines kind of move, people are actually very good at that. It kind of pops out and they can see it. So we do something called a convolutional neural network. You'll have to ask Lynn what that is if you don't know. And but it has 3D convolutions, so it's actually sort of convolving in both time and space. And so it's a giant model. Well, it's not even that giant. It's a model that is trained to produce this output mask. So every time it sees a series of 6 frames, it'll try to reproduce what the judges said were the contrails. So that works pretty well. We get about a 70% recall and precision when we use multiple frames, and that's certainly good enough for our purposes. And you can check the contrail density. So if you just plot over, I think it was a year, just the density, how often do our contrail detectors detect something? You can see all of the major flight paths over North America, which is very pleasing. So it isn't just random. You see like people flying from Los Angeles to Japan or down to Hawaii, or maybe this is Hawaii and this is down to New Zealand or Australia, and maybe that's way up to Japan, or just all of the routes on the East Coast United States. And so that's, again, that's an open sourced data set if you want to play with it yourself. So how do we do contrail forecasts? I trimmed this talk down, but essentially you have to answer two questions, one of which is whether if a plane flies through a region in the atmosphere, whether it'll make a contrail at all. So it's like if in statistical language, that's P of contrail. And then given that we predict a contrail, how bad of a contrail is it? So that's like the expected value of the radiative forcing given that there's a contrail. And the way we do this is with yet another neural network. And this we use a ice microphysics model from DLR, which is the German aerospace lab. It's called COSIP because it's just very difficult to predict. It's very difficult to observe directly the warming due to contrails. We're working on that, and we have a paper in progress, but it's difficult to pull out the warming due to one contrail. So we have to use a model for that. And then what we do, in effect, is publish a live map, which we then give to the airlines or give to the flight planners. So these red zones are regions where contrails are likely, and if there was a contrail, it would be very warming. And then this is a 2D map, but of course they're actually 3D maps, so there'll be altitudes so they can route around them. So for example, eventually there are these channels I don't know if you realize this, when you fly over the North Atlantic, there are these pathways that are defined by the air traffic control, and we might be able to help them move them away from where the contrails are being made. So let me finish the story by telling you the study that we've done with American Airlines, which is unsurprisingly an airline in the United States, how we worked with them to actually prove that our contrail avoidance actually is, we can avoid a statistically significant amount of contrails. So they came up with this we all jointly came up with this very clever study framework. American Airlines is based in Dallas-Fort Worth, and so that, we had 10 pilots that we worked with, and they would go from Dallas-Fort Worth out to some city like Seattle, or Portland, actually, it looks like Portland, and then come back, right? Or they would go out to Los Angeles and come back, or go to, Acapulco and come back. And so that is what they call a match test, if you're data scientists, where that when you land, the people coming in off the plane and they take off, the weather is close, not identical, but pretty close. The atmospheric conditions going down and going up are pretty close when you land and take off because they're close to each other in time. And so we used those to be the matched tests that we randomly assigned either on descent or ascent, avoid the contrails. And in fact, what they did, although it was largely up to the pilot, what we told them randomly, either on ascent or descent, avoid or don't avoid. And then we gave them a map. I'll show you the UI. And then what they did is, when the control group, they tended to fly up quickly and then cruise and then fly down. By the way, you can see the way all across the whole world is like planes don't fly at arbitrary altitudes. They fly at, it's kind of funny. It's always 1,000 feet, essentially an integer of 1,000 feet. Even though it's imperial units, but that's just the way that aviation works. Sorry, but so they would normally in the control they would fly up quickly and then go to cruise. When it's a treatment, they would go up a little bit or go down a little bit faster, or go up a little bit slower. Like if there was a contrail up here, they would avoid it by just going more slowly. So again, we were randomly assigning them treatment or control, and so we had, by the time we did all the experiments, we predicted these things called contrail likely zones, which are these regions, and we had 22 pairs, which when the contrail likely zone existed on both the ascent and the descent. And so then we had, we had 22, we had n equals 22, which is not very much. To show you what would happen is we built a user interface. So this would be something like the probability of contrail or the expected value of the warming of contrail. And so then the pilot would decide, oh, well, I'm going to go, and I won't quite go as high. I'll go to flight level 320, and then I'll go up to flight level 3. We can't really force them. The absolute requirement for pilots is safety. So we can't tell them do this, do that, because they're responsible for the safety of the flight. So we tell them, please, avoid contrails, but they get to decide exactly what to do. So we gave them this UI, and we have n equals 22. And it turns out, and then we checked for those n equals 22, we did verification. So this is what I was referring to, that here was the flight path of one of the flights. And then when you let it blow with the wind over 15 to 30 minutes, it matches up with an observed contrail in our detector. So that was like a positive match. So so we measured the number of contrails in that n equals 22 set. And fortunately, we actually got statistical significance, right? So on the control group, we found about 50% of them had contrails. And when we actually said avoid the contrails, we increased that from 11 to 18 and decreased this from 11 to 4. So that's about 54% of the contrails. So this is statistically significant at 0.05 because it's a match test. And we've actually showed that we can statistically significantly reduce contrails. So that was exciting. And now we're working with airlines and flight routing software people to get this, to make a larger scale test and to hopefully get this into the real world flights. Okay, so that's it for contrails. Let me spend just a few minutes telling you about a different project, which is fun, has nothing to do with aviation. Well, it actually does have something to do with aviation, but it's something called Project Sunroof, which is estimating the amount of solar power that a house can produce, but we use AI to do it. And this is like a short mini talk. So Sunroof is a product that Google has actually been shipping since 2016. What it is, in fact, I think this is the person who started it. You can go to a Google website and look at your city. Well, okay, now maybe it'll work in Europe, but it used to be just in North America, and only some cities, where you can actually measure, or it would estimate how many kilowatts of, if I put solar panels on my house, how many kilowatts would it produce? So it needs to know a couple of different things to make this estimate. It needs to know how big your roof is and which angle is it facing, because it computes, again, in the northern hemisphere, how many watts would you get when the sun is low and how many watts would you get when the sun is high. And it would just compute a number of kilowatts. It also measured the shading. So if there were trees or other buildings that would block the sun at different, it did it at two different times of the year, the two extremes. And then it would get an estimate of how many kilowatts it would make. Now the big problem is, what you need to make this work is you need, there's something called a DSM, a digital surface map, which is how high is any point. So any pixel has a height and it's encoded in color. And if you have a high quality DSM, you get something like this, and you can see, these are houses, and you can see the roofs. You can sort of, eyeball where the roof segments are and how big they are and which way they're angled. The trouble is, you only have high quality DSMs when you have airplanes. Little airplanes fly over individual cities. And so, for example, in Europe, we only had that on this map. I mean, yes, you probably got Berlin, but if you were in some small town or away from the major cities, we only had low quality data. This is what the low quality data looks like, which is kind of terrible, right? You can't really. It's the same location, and it's just okay. Those look like buildings, I guess, but you can't see the crisp roof lines. So AI to the rescue! You can learn to map the low quality DSM into the high quality DSM. That's what we did. We had a very nice architecture called a UNet, I highly recommend it, which took both. Ooh, what happened? It's not advancing. Huh. I wonder why. let me do read. Yeah. Oh, no, it went away. Oh, here, let's redo it. Big boy. Lionel Messi wants you to have solar power. Okay, here we go. There we go. So there's something called the architecture I'll show you called a UNet, which takes these low-quality digital elevation maps, the high-resolution satellite images, which go down to centimeters, and then also Google has metadata about where all the building footprints are in the world, and it tries to predict from this bad data, it tries to predict the good data, and then it tries to do essentially graph cut, which is an algorithm to kind of chop up the planes of the digital elevation to try to make these planes that are the roof angles. Here's a picture. I really like the UNet architecture. We can talk about it. What it does, it starts at high resolution, and it tries to generate a new image at that same resolution, but it makes multiple resolutions of multiple representations at different scales. So this is like 1/4 scale, 1/8 scale, 1/16 scale, 1/32 scale. So it makes representations at ever coarser scales, tries to reconstruct it, and then makes an output as a combination of all those scales. So that's a neat. We didn't invent it. Actually, I'm not sure who invented it, but my group certainly didn't invent it. So it shipped in August. You could see, by the way, from the DSM that you can actually emulate what happens with the sun as it sweeps through the morning to evening. So you can actually tell when you're shaded by other trees or other buildings. And again, that now increased the land coverage by 13 times, and we've added more than 100 million new buildings. And this was the team that did it across Google. So that's actually shipped. And so now we have solar installers go to this website. That's who it's aimed for. Although consumers can use it too, but solar installers come and they use it to tell the consumer, hey, I can come to your house, and if I put things on, you'll get 4 kilowatts. And then they say, oh, because if they don't know, it's like maybe I should buy solar panels, maybe I shouldn't, I don't know. But if you can actually give them a number, and then it tells them like how cost effective it is. So the solar installers love it because their customers become much better informed. So that's the end of the talk. I'm certainly happy to answer questions, but I just want to say that when you add AI to remote sensing, from airplanes or satellites, it can be a very wonderful tool to fight climate change. So thank you, and I'm happy to answer questions. Any questions? Or there's a question in the back.
Hi, thanks for this great presentation. And I was wondering, when it comes to working with companies to try these kind of things, of course, I guess Google has a lot of leverage to do this kind of thing, but other maybe government entities or NGOs and stuff like this would have less of that. So I'm wondering what kind of negotiations went on with these companies, just to learn what kinds of things can be used to leverage this, to convince these profit-making organizations to contribute to this kind of project.
Well, I think it's very different from sort of, policy regime to policy regime, right? I mean, the United States is much looser about carbon than the EU, for example. So, in fact, our approach has been different, right? And in fact, it's also different not just because of the policy regime, just because of the density of the airspace. In the EU, you saw on the pictures how tight, it's very tight. So we can't really work with the individual airlines in the EU, because if we said, oh, EasyJet, I'm picking, not that we do, I flew from Rome to EasyJet yesterday, so I pick them at random. EasyJet, they'll fly this way. They sure, so okay. Someone else will just come, Ryanair will come and just fly back. So we really need to have a centralized air traffic thing in the Europe, because it's just so dense. Otherwise, we can't do it individually. But interestingly, the airlines in the United States, it's not like you might think it's a free-for-all, but they do feel pressure, and they know that original graph. They know it's very difficult. They're trying to do sustainable aviation fuel, extremely expensive, and also somewhat carbon dubious. There's some sources, I was telling Lynn, there's some sources of sustainable aviation fuel that are made out of animal fat. Now, if you know that you take petroleum, you turn it to grain, you turn it to animal, you turn it to fat, then you turn it to fuel. You might as well have just turned the petroleum directly, and it's waste, but it's very difficult to know about the additionality of that. So sustainable aviation fuel is very difficult and very expensive. So the airlines we've spoken to are actually, we're not pushing, it's not like we're shaking our finger. They know and they feel pressure. There's ESG investing, and there's public pressure on them to do something. So yeah, we've actually felt pull from the airlines. It hasn't that we've begged them. I mean, maybe we begged them a little, but they actively want to help, because they know they have a big problem, and it's extraordinarily expensive to decarbonize. So if they can get rid of 1/3 of their warming very quickly, they are very happy. Go ahead.
Yeah, thanks a lot. Really, really interesting. So 2 questions. The first, a bit more from my understanding. So I guess like sustainable aviation fuels are the future long term. Are contrails still produced by them? I guess so, right? So
Yes.
The solution would then basically be relevant also post 2050, once we have potentially fully put SAF into airplanes, that avoiding contrails will still be a need basically after that.
That's right, because
Okay.
as long as you're dumping even a little bit of water, and when you burn any
Okay.
fuel, well, even hydrogen, right? Even if
Yeah.
it was purely hydrogen, you'd be making water.
Okay, thanks. And the second point, so so I was just wondering, to avoid those contrails, you basically reroute the planes, but planes are following a specific route for a reason, usually because it's the most fuel efficient
Yes.
route. So are you taking into account that rerouting might actually be increasing fuel usage, and how relevant is that increase in those CO2 emissions due to increased fuel use compared to the
Thank
CO2
you.
and the global potential avoided?
No, that's very good. I left that out of the talk, but it's an extremely good point. Yes, no, we're very sensitive to that, because the airlines still are, there's both the CO2 from the fuel, which is bad, and it turns out that they're cost sensitive, so they don't want to spend more of the fuel. So in our experiment that I listed here, it would have been the equivalent of about 0.3% of if we extrapolate from these 22 flights, it would be about 0.3% of the fleet fuel increased, which surprisingly, the airlines are not perfectly optimal. They have, a 0.2, I mean, they may be suboptimal by roughly that thing anyway. So that's sort of just in the noise. And then when we checked the CO2 equivalents on 100 years, it's definitely much more of a win for the climate to prevent the contrails compared to the loss of the extra little bit of CO2 from the fuel. Sometimes you're lucky and you actually get a little bit of fuel back. That doesn't happen very often when you move it. But yeah, it's actually we've checked, and it's a tiny fraction of the fuel. If you think about it, optimally, depends on how accurate I showed you those ROC curves on the detector. There's also an ROC curve on the predictor. If you have to spend a couple of more percent of fuel on 3% of your flights, which is very difficult to attain, but let's say you can, that's 0.06%. Maybe you can't. You do a couple of percent of extra fuel on 10% of your flights. That's again the 0.2%. So yeah, it turns out it's just a tiny extra fuel cost, and so they're content with it. Yes. Sorry. Sorry. I should probably follow the microphone. Yes, please go ahead.
Hi. It was really interesting. Just wanted to know, like, have you considered the maximum takeoff weight or the load factor into consideration?
Maximum takeoff weight. So it turns out that you mean, so I guess there's two possible, I'm not sure which question you mean. Do you mean in predicting
So,
the
like,
contrails or?
yeah, like as an independent variable of the model, maybe. So, did you consider the weight of the aircraft which you experimented on?
No, because we left this up to the pilots. The way that UI, at least for the test, is given to the pilots the same data that they do to avoid turbulence in real time. So a lot of the fuel loading is decided sort of beforehand. Now we're working trying to get it be upstream so they can optimize, right? Oh, you'll have to fly like this, which flight planning is an incredibly complicated thing, which Google doesn't do. But there are super experts in the world who do it. So we're trying, it turns out that we can predict contrails like the night before with relatively good accuracy, precisely because it turns out that these ice supersaturation regions don't mix very rapidly. They just sort of float around for hours and days. And so it turns out we don't need to do the prediction like an hour before. We can do it 8 or 12 hours before, still at very good accuracy, which then allows us to tell the flight planners, oh, avoid the spot, which then allows them to determine the takeoff weight. In other words, go into the gigantic optimization. But we don't actually do the gigantic optimization because we are not experts. We just supply maps like or UIs like don't fly here, and then let them figure out. Again, safety is an enormous consideration. So interestingly, by the way, the fuel efficiency of the jet actually is an important contributor to, this is what I thought you might be asking, to the radiative forcing. Because it turns out that it turns out like the more soot you make, the less efficient engines actually tend to make more contrails. So it's kind of interesting. But that's not what you were asking. Okay, now you can go.
Yeah, hello. Very nice talk. I just wanted to know that you briefly mentioned the role of AI-powered remote sensing in addressing climate change, and like you spoke about how to deploy convolutional neural network and Bayesian deep learning models. But these network architectures, they themselves are like infamous for their intensive computation process, right? And they require large amounts of data set. So to address the elephant in the room, how does like big tech intend to tackle its own carbon footprint of minimizing computation related carbon footprint like CO2 emissions? What is Google doing?
I think there's a lot of misperception around this, which is quite unfortunate. So that convolutional neural network that's been running, we have it running 24 hours a day. For a moment, for argument, assume that we don't use any renewable energy. I'll get to that in a minute. That convolutional neural network, I checked, is the equivalent of 20 kilometers of contrails. For a year. So everyone says, oh no, it's so giant. It's one contrail. So when you're, the ratio, the return on investment of oh, I'm burning some CO2 in theory to run these computations, it's no question. I mean, it's several orders of magnitude of benefit to the cost of the compute. Now, Google, there is a larger issue here, but the right way to think about it. So it was very interesting. Dr. Huck and I were on a panel at the Clean IT conference, and Professor Rockstrom from PIC said something very wise, which is, look, this is electricity. We use electricity to run computation. That's actually not the problem. It's the actual fuels and the heat that's the problem. So what Google does is we are, again, depends, we have to be very careful about what we mean. I can say we are carbon neutral. What I mean by that specifically is that for all of the electricity we use in operations across the whole world for a year, we buy that much renewable energy. That is good, but is only good before the world is decarbonized, because there's sometimes when we give extra and we give it just out to the grid, because grid electrons don't know whether they came from renewable energy or not. So as long as things are mostly not decarbonized, it's good. But we're striving for 2030, because by then it will start to get very constrained, to be what they call 100% carbon-free energy, which is for every hour in that location, are you buying enough renewable power? That's much harder because we're a worldwide company, and there are just places that just have very little renewable energy. By the way, in Germany, we are already at 96% CFE, so there's a few percent left. There are other places that are much worse. We're about 67% overall. So the right way is not to say, oh, big tech is doing all sorts of carbon. No, I think Google's the best, but to be fair to my friends at Microsoft or Amazon, they're also trying. All of the companies are trying, because it's not, again, it's not like aviation fuel. It's just electricity. So it's actually good. In fact, if you look at some of the work by the economist Jesse Jenkins, when companies have these 24/7 commitments like Google, there's actually a network effect. I can find the paper for you if you like, where it actually stimulates, because we're not just saying, oh, we're going to be carbon neutral, but we're actually going to match every single hour in every single location. It actually forces the grids. We're a big customer, so we shout at the electricity providers to force them to be more renewable than they otherwise would. And again, there's economic models that show that there's a network effect of about 60%. And it's like you're more powerful than you would be by 60%. So yes, we are buying renewable power to power all our stuff, and we're working. It's actually not trivial to try to scrape up and buy and purchase. And I don't know if any of you are into electricity policy. Electricity is enormously complicated. I don't do it myself, but friends of mine buy the electricity in Google worldwide, and the number of regimes of electricity purchases is just, oh my, it's a gigantic headache. It's not like there's one model in the world. It's so many different ways of buying and selling electricity, and governments and companies. Anyway, so, just to say, I think it's a bit unfair. People are saying, oh, it's really bad. No, it's just electricity. We're working on it. We're 100% carbon neutral, and we're trying to go beyond that to be 100% carbon-free energy.
That sounds great. Thank you.
Okay. Oh, gosh.
So thank you very much for your talk. I don't know if you have a few minutes to stay around.
Oh, yes.
I don't know if we
Yes.
need to also liberate the room.
I think we do.